Hello, welcome back. I'm Jason, and today I'm going to teach my most controversial lesson ever, and that is why exactly does an airplane wing generate lift, or how does an airplane wing generate lift? Now, the reason I say it's controversial is because we've all been taught how this works incorrectly when we're younger, and I'm going to go over that here as well. I was taught incorrectly, and almost certainly you were taught incorrectly also, unless your parents were like wind tunnel experts or aerodynamicists or aerospace engineers, right? And the reason it's done that way is because it's simple and intuitive to understand, but it isn't really correct. So what I would like to do today is go through the details so that we really understand it. All right, now before we begin, I'm just going to go ahead and say up front that I'll be talking a lot in here about what it feels like to stall an airplane wing and kind of what that feels like. And so I am a pilot. I'm an instrument-rated private pilot. I'm not a fighter pilot or anything like that, but I've flown airplanes before. So I know what it feels like when a wing stalls, and that's part of the reason why I'm so interested in aviation anyway and how wings work is because I like to fly airplanes. It's been a while, but that's something I've done before. Now, secondly, I want to go over the big picture plan so you know what I'm actually doing from a big picture point of view, so when we get to the end, you'll know exactly how we got there and what we've actually covered. So the first thing I want to do is I want to go over the existing wing structure that you've seen, explain what most people are taught when they're younger, how wings generate lift, and explain why it's not correct. Then the next thing I want to do is I want to go over 3 or 4 different mechanisms that's involved in the wing that each contribute to the lift. It's not just one thing. That's why it's so hard to explain why wings fly. It's actually several things coming together. And then next, I want to get all the way down to the molecular level. You can talk about fluids, that's really important. You can talk about pressure, that's important. But don't forget, pressure is a macroscopic quantity with an ensemble of trillions and trillions of molecules. So the individual molecule is where you really start to understand the mechanisms causing all of this stuff. And then after I get down to the molecular level, putting all of the mechanisms in place, I'll combine them all together so you have a really good understanding of how it works. And lastly, I want to start simple. That teardrop shape that you've all seen for an airplane wing and how it's explained how they fly. That shape is not necessary to generate lift. So I'm actually going to start by showing you a flat wing like this thing right here. And you all know that paper airplanes fly. You know that these little things fly. I mean, I can get over here and just do a 1, 2, 3, throw it. And you can see that lift was generated from that flat wing with no curvature on the top. So we're going to start with that because then you can isolate the different parts of lift. When we get to the end of it, we'll be looking at the traditional teardrop shape and understanding why it was designed that way when we wrap it up in a bow and understand all of the components contributing to lift of an airplane wing. All right, so we need to start with our common ground. I'm going to explain to you how I was taught, even in flight training, on how an airplane generates lift. And it was probably pretty close to what you were taught. But we're going to pick it apart and we're going to find out that it's not correct. All right, so here we go. Usually an airplane wing is drawn with a flat bottom and a rounded nose that comes to a fine point at the end, something like that. Now, right off the bat, I'm going to say that this is not a great picture to understand lift, and I'm going to show you why in a second. In a real airplane, when you're flying, the wing is almost never presented like this, where the bottom is flat to the incoming relative wind. Usually, there's what we call an angle of attack in aviation. It has a cool sounding name, but what it means is that the wing is angled up to the relative wind. So if this were the airplane wing, if this were the bottom surface of the airplane when we're flying this direction, you're almost never flying with the wing like this. You've tilted the entire airplane such that the wing is angled at something like this in general. And when you're flying really slow, the wing might be angled like this. When you're flying really fast, you might have it more shallow like this. But it's a good diagram to start, but I want to let you know that you don't get the full picture from drawing an airplane wing in this configuration. But we are going to start there because it's how most people are taught. So what you have is you have some wind coming in here. You have some propeller, some jet engine or something pushing you one direction. So you have some wind. Now really it's called the relative wind because you really need to be picturing that you're standing on the airplane wing or in the cockpit. You pretend that you are motionless and then that wind is rushing toward you even though you're the one flying through the air. So here the wind goes and does its thing. Now, it encounters the front of the wing here. Now, of course, we have some streamlines of the fluid that are going to pass right under the wing like this. Some of the streamlines are going to impact and kind of be guided around like this. And some are going to kind of bunch up and kind of like just kind of stagnate there. And then some are going to kind of go underneath like this. But the flow is essentially going to split as it goes over the top and over the bottom. You were probably shown a drawing something like that. Now, eventually, the flow is going to continue over the wing like this, and it's going to recombine with the flow that's on the bottom right here. So you could say like right here, it recombines, right? Right? Now, what we're all taught, or at least what I was taught, and what you were probably taught, is that this distance from here to here is some number of meters or centimeters or whatever. And this distance, because this is a curved surface and kind of curved down like this is a longer distance on the top. And what you're taught is that the flow, when it splits, takes the same amount of time to go from here to the end as it does here around. It's called the equal transit theory. That's what it's called, equal transit theory. It's the fundamental reason why you were probably explained that airplanes generate lift. Because when this flow splits, you're taught that the flows go up and down and they end up in the same spot over here at the same time, right? And because of this top thing, this top path here is longer. I'll actually put here longer path, and this is a shorter path, right? And because they meet up at exactly the same time, the only way this can happen is if the top flows faster. And this is slower. So you're taught that the airflow splits and the airflow over the top of the wing moves much faster than the airflow across the bottom because they recombine at the same time at the same point right there. And because of Bernoulli's principle, remember Bernoulli's principle basically says that fluids that are moving faster have lower pressure and the fluids that are moving slower have higher pressure. So because the top flow is moving faster, we say that there is lower pressure on top of the wing and higher pressure on the bottom of the wing. And pressure is just force per unit area, like newtons per square meter or something like that. So if you have a high pressure region on the bottom of the wing and a low pressure wing on the top of the wing, that's like a difference in force or pushing force across the surface of the wing. And so because it's higher on the bottom and lower on the top, what we're all basically taught is that this generates some lift, right? Some lift vector, which is pushing up on the bottom like this. And it purely comes from the difference in the pressure on the bottom and the top. And that comes because the fluid is traveling slower on the bottom than it is on the top. And that comes because of the equal transit theory that the flow splits and it has to recombine at exactly the same time there. And this path is longer, so it has to travel faster across the top. That is what we are taught. Now, I don't claim to be the smartest person in the world, but I can tell you with certainty there is no law of physics that says the equal transit theory must be obeyed or that there is an equal transit theory. Basically, the fundamental core nugget of what this picture is designed to teach you is that basically because the flow meets up at the same time, it must be going faster across the top, and that leads to the pressure difference. But there is no law of physics that says that this flow must split and recombine at the same time there. That law of physics doesn't exist. And in fact, it's not even true. I'm going to say that again. It's not even true. I'm going to say that a third time. It's not even true. The equal transit theory isn't true. You can go and find videos of wind tunnel experiments that do a puff of smoke and watch the flow split and come back down. It is true that the flow does travel faster across the top of the wing. But it is not true that they recombine at the same time over here. That is not true. That is demonstrably and experimentally falsified. It isn't true. Now, I don't like to bag on explanations like this. Honestly, I actually kind of like the explanation. It's great for young people because you learn about Bernoulli's principle, you learn about pressure and the difference in pressure leading to a force. There's a lot of fundamental things there that are really great in this explanation. And it's digestible by most people if you sit down and break it down. The problem is real life is more complicated than we'd like it to be. And because the equal transit theory isn't correct and it's not a fundamental law of physics, then we can't rely on it to explain this. The equal transit theory is not correct. However, a lot of the things you know about wings are correct. For instance, It is true that there is lower pressure on the top of the wing. That's true. It is true that there's higher pressure on the bottom of the wing. That's true. It is true that the difference in these pressures generate the lift vector upward. That part's true. It is true that the flow does flow faster on the top of the wing and it flows slower on the bottom of the wing. All of that stuff is true. But what is not true is that the equal transit theory says they have to split and come back at the same time. That's not true. In fact, as I mentioned before, in wind tunnel experiments, the top flow gets to the back here about 20% faster than what's happening on the bottom. So it's not that they recombine at the same spot, that it actually gets there even faster than that. Okay, but I wanted to say all of that in one spot because I wanted to tell you that I think the reason why that explanation is so popular is because it does get you to remember all of these things. So all of these things in this list are true, but they're not true because of what you've been taught before. They're true for other reasons that I'd like to teach you today. What we have to do is actually go into the fundamental parts of physics. That's what I mean when I say get down to the molecules. You have to look at how the molecules are interacting, which is the fluid flow theory, right? Fluid mechanics. And you also have to go and talk about Newton's laws. F equals ma, force equals mass times acceleration, and also equal and opposite reaction. We're going to talk about all of that here. So now that I've kind of like talked about why this isn't true, then now what we have to do is tear apart this wing, stop looking at the beautiful teardrop shape, and go back to the root basic of a more simplified wing, and I can prove to you that that simplified wing can generate lift even when the top of it is not curved like this. And then you will be able to finally dispense with this as being the explanation, because if I take away the curvature and I show you that you're still generating lift, then you'll be forced to say, okay, that can't be the explanation. There has to be more to it, so let's do that right now. So they say a picture's worth 1,000 words. I think a 3D prop of some kind is probably worth 1,000,000 or 1,000,000,000 words. This is an aircraft wing. If you go look at made of wood here, and it's flat. There's no curvature to it. It has some thickness, but very little. If you go look at the original pictures of the Wright brothers airplane, there's a tiny curvature on the top, but I think it was mostly accidental. They're mostly flat wings. And I want to show you by really analyzing this that curvature on the top of the wing is not necessary. But there's a very good reason why we don't make wings actually flat like this, except in the case of like supersonic airplanes. That's a totally different thing. Those are generally a little bit flatter, okay, for other reasons. So here we go. We have 3, 2, 1. Let me throw it one more time. And you can see that that airplane definitely flew. It was generating lift without me, without having a very exaggerated curvature on the top. So we have to figure out why, because that's part of the reason why an airplane wing on a commercial jet generates lift, at least part of the reason. All right, so let's do that. Let's talk about that. So I'm going to call this the simplest wing. I'm going to call this the simplest wing. All right, so first let's take the example of a flat piece of plywood or a flat surface like that that is at some kind of angle. Let's do it over here. Some kind of angle like this, a shallow angle, right? And remember what I told you, in real airplanes, there's always an angle of attack. If you look at airplanes, they are the bottom surface of the wing is usually not designed to be totally parallel to the path of flight. When you're flying, usually the nose is up a little bit, and so you present the bottom of that wing flying into the relative wind. So I'm going to draw this flat plywood wing with some angle that says an angle of attack here, this angle here to the relative wind right here. Now the relative wind, just like it is for any airplane, is hitting the thing like this. I'll put one giant arrowhead like this. Bunch of different streamlines interacting right there. Now what happens at the molecular level when one of these molecules of either oxygen or nitrogen or water vapor, carbon dioxide in the air, goes and impacts the bottom of the wing? What do you think will happen? Well, it's going to bounce off. Let's say it bounces down. In reality, depending on the angle, it might bounce back at a kind of an angle like this, or it might bounce back at an angle like this, depending on what you're doing. But let's say it bounces off straight down. So there was a velocity of the molecule this way, but now there's a velocity going down. You have changed the direction of the velocity. I'm saying that because it's very important, and I'm going to get back to it in just a second. All right? So how do you think, well, what do you think will happen? If it bounces off of it, then you can imagine, just like just like if I tell you to hold your hand and I throw a baseball and it bounces off, and it bounces off in a downward direction, your hand is going to tend to fly backward because it's hitting this way, but it's also going to tend to fly upward a little bit. If the angle is like this and I hit you like this, probably you're going to go up like this. There will be a component in the upward direction hitting your hand. That's basically the lift force or the lift vector generated by this. Because whenever the molecule hits right here, the surface of the airplane wing is basically redirecting the momentum or the velocity of this thing downward. It's basically swatting it downward. So there's a force right here pushing this and changing the velocity vector down. There has to be a force to change the direction of any velocity. You know, inertia, object in motion tends to stay in motion unless acted upon by an outside force. So when this wing slams into the molecule and redirects it down, there must have been a force from the airplane wing acting and pushing the air molecule down. Remember Newton's third law, action, reaction. So as the wing acts downward on the airflow, the air molecule itself acts with an opposite direction force acting up on the wing. Remember, action-reaction pairs act on opposite bodies. They never act on the same body. If I push with my hand on the wall pushes back on my hand. If a rocket exhausts out this way, pushing on the molecules of the exhaust molecules push back on the surface of the ship, thrusting it the other way. So whenever the molecule hits this, there's a force pushing it down, the force of the interaction. Wing acting on molecule. The reaction force is molecule acting on wing, and that means that there is going to be some component of lift in the upward direction, the force right there. All right? Now, when it's very shallow like this, there's not very much force. You can imagine the wing being totally parallel to the wind flow. There's no force at all. But if I tilt it a little bit, you start presenting the bottom of this thing to the relative wind and redirecting downward like this and generating a small force. And as I increase more and more and more, eventually you get horizontal, where I'm flying into the or vertical, I should say, flying into the relative wind like that, where again, you don't get any force anymore because you're not redirecting anything down. You're just smashing into it. So when you're totally horizontal, you don't get any lift. And when you're totally vertical on the wing, you don't get any lift. Somewhere in the middle must be an optimal angle to adjust this thing at, the angle of attack, right, for a flat wing airplane like that, where it's generating lift in the optimal way, right? Now let's increase the angle just a little bit and see what happens. Let's say you increase the angle just a little bit. That's supposed to be a little bit more steep of an angle than that one. Maybe it's not perfect, but you get the idea, right? And so you have the wind hitting this thing. So what's going to happen? Well, you're going to have your molecules go and basically be redirected downward. And so they were traveling with some velocity here, and now they're traveling with some velocity here. Anytime you change a velocity, there must have been a force involved. And I'm going to get to that even more detail a little later. There has to be, because inertia, it's always going to go in the same direction unless some force acts. Wing acting on molecule, then the reaction force is the molecule acting on the wing. So there's some upward lift there. But here's why I redrew the picture. Because the steeper you get this thing, then what ends up happening is some of the wind encounters the leading edge and kind of goes over the surface like this, and it creates a little turbulence right there. When the wing is very, very flat like this, and the wind is going over it like that, it's extremely smooth with no vortices, but it generates no lift. As soon as you start increasing it a little bit, you start generating lift, but you start generating drag, because this over the top, the flow is interrupted, and it's basically causing drag right there. At the same time that you may be generating more lift. I could have drawn the arrow maybe a little bit more, a little bit higher. Maybe when it's like this, your velocity is really like this, and so maybe your force is maybe a little bit higher. But in the course of generating that, you have some drag right there. By the way, I haven't drawn it, but there is, this is the reaction force. The action force on the molecule would be here, action, reaction, and the force acting on the molecule here would be action, reaction. So when the velocity changes direction, there has to be a force pushing that. The reaction force is the molecule pushing up on the wing, and you're generating drag there. Now what's going to happen when this thing becomes very steep, like this? You can already tell from your own intuition that this thing is not going to generate really, it's not going to be a good wing. Because what's going to happen is we can all intuitively tell that when a molecule hits this thing, it's not going to generate as much lift here. So you're going to have a downward force there, but there's basically a ton of drag because you're smashing into the wind horizontally like that. And so what's going to happen is you're going to have an upward force, but maybe not as much. So you may have a maximum force at the perfect angle, and then less and less force on either side of that. Now what's going to happen at the leading edge of this wing? The flow is going to get here and it's going to do all sorts of things. It's going to generate vortices around this thing, which are going to spiral out and cause drag. So you're going to have to imagine a bunch of different parallel, streamlines interacting with this thing. Trillions and trillions of particles generating tons and tons of lift right here. I'm sorry, drag. Less drag here, maybe a tiny bit of drag here. Totally flat, no drag at all, but you also don't get any lift either. So this is why we really don't use flat wings in aircraft, because they do generate lift, but they generate a lot of drag. And what happens when you have drag? Your engines have to work harder to pull you through the air. So this is the basic idea for the flat wing there. And I can tell you that even in small airplanes that you fly with curved wings, there's something that you learn how to do early in pilot training called stalling your airplane. Now, that means you're way high in the sky, usually 3,000 feet, and you pull the power back slowly, and then you pull back on the control column a little bit more, and what you're doing is you're increasing the angle of attack of the wing. And this is with a curved wing, with a regular curved wing there. But what happens is you eventually reach a critical angle of attack where the airflow is no longer smooth over the leading edge. And you lose lift because you're generating all that induced drag there. And what happens is you lose lift because you're traveling slow at a very high angle of attack. You're generating lots and lots of vortices or eddy currents, whatever you want to think, what word you want to use. On the top of the wing, it interrupts the airflow and you lose lift drastically, and then the airplane stalls. Now, that usually means that the nose drops and you pick up speed and then you can recover. But if you stall really close to the ground and you hit the ground, then you crash, right? So that's really bad, especially in bad weather. You want to really work hard not to stall your airplane wing, which means you can't go too slow while pulling back too much and increasing that angle of attack. Now, I'm going to write one thing on the board now that I mostly want you to keep in your mind as we continue the talk here, because I'm going to circle back to it later, but I want to set this in your mind early on. Notice that we had horizontal velocity, we redirected to a vertical velocity. Horizontal velocity of particles of air, we redirected to a vertical velocity. Horizontal particles of air, we redirected to a vertical velocity. We changed the velocity vector, we changed the velocity. Okay. Now, you may or may not know this, but basically changing a velocity, you know that momentum in physics is mass times velocity, right? So if you change the velocity, you're effectively changing the momentum vector of the airflow. It was horizontal, but you changed it. And anytime you change the momentum of a particle, there must be a force involved. That is directly tied into Newton's laws. I'm actually going to write it for you in a minute, but I don't want to get too far ahead of myself. You can say that the change in the momentum is equal to the force. And I want you to start to think of these velocity changes instead of just changes in velocity. I want you to think of them as changing the momentum of the flow of the entirety of the flow of the air underneath, from a horizontal directed momentum to a vertically directed momentum. Now, of course, all of the air is not going to go straight down. Some of it's going to hug the bottom and come off the back. Only some fraction of it is going to be directed down, but still, anytime you redirect velocity, you're changing the momentum. And in physics, you learn that any change in momentum is equal to some force has to be there in order to change the momentum. That's what I'm really trying to say. And I'm going to talk more in more detail about that later to make it clear. So I hope now I have proven to you that even a flat sheet of plywood connected to an engine and a light enough frame can fly. The problem is it's going to generate a lot of drag as soon as you pull back and increase the angle of attack, generating tons of eddy currents across the top. So how do you make a better wing? Well, it might be a good idea to take a look at the leading edge, because that's where all the drag, or at least a lot of the drag, was generated. What if we rounded the leading edge of the wing? What if we turned it into a bullnose kind of thing, that it was kind of smooth in the front and didn't totally just so abruptly disrupt the airflow? Would that decrease the drag? Would that make it better? Yes, and that is why the shape of airplane wings is rounded in the front and tapered to a point in the back. So that's where we're going to go next. Okay, so here we go. We have that flat bottom that you know of. and then we have that rounded thing right there. And the wind, relative wind, is coming this direction, something like this, right? And you might guess that some of the wind is going to go over the top and some of the wind is going to go underneath. It kind of splits there. Of course, the particles that are already down here are going to go straight ahead. The particles that are up here are going to go barely skimming and mostly go straight ahead. But some fraction of them are going to hug this shape as it goes across. I'm going to talk more about that in a second. Now, before we talk about the leading edge, I want to actually talk about the trailing edge, because I didn't do that yet either. There's a really good reason why the trailing edge of the wing is tapered to a point like that. Basically, you want the flow, when it comes back, to rejoin in a smooth way without generating a bunch of eddy currents, because those vortices like that, the swirling effect of the air smacking into the wing also leads to drag, right? So you might imagine some wing that you might design which would have the same thing in the front, but maybe be rounded in the back instead of a point like this. And what would happen is the flow would come over here, but it's going to try to hug the surface here. It's not going to detach well. Eventually, it's going to break away and start to do this number and do a bunch of curlicues and a bunch of vortices in the back, and that is going to be drag as well. So I just wanted to point that out before I forgot it. This is the reason why the trailing edge is almost to as fine of a point as possible to allow the flow to detach from the wing cleanly without any vortices. And I'll tell you, by the way, I used to work on plasma rockets for a little while, and it's the same thing with magnetic fields guiding plasma out the back of a rocket. You want a clean detachment of the plasma from the magnetic field. And there's a bunch of tricks to try to do that, because if you don't detach properly, you end up dragging the rocket in the wrong direction because the exhaust doesn't want to detach from the rocket, and then that's counterproductive. And you want the flow of the air to also detach from your airplane wing, because if it doesn't, then it's going to slow you down. It's like flying through syrup or something. If you tried to fly an airplane through syrup, and nothing detaches from the wing, it's just going to get stuck there. It's an extreme analogy, but hopefully you get the idea. So the trailing edge is pointed for that reason. So without further ado, I'd like to draw a large diagram of a wing and try to get most of this explanation out so that we can put it all together. Okay, so that's mostly the shape of your airplane wing. All right, and as you know, on the front, you have these streamlines, which are parallel, velocity vectors of air, which is a mixture of gases, by the way, lots of different gases in the air, impacting the front of the wing. Now, the ones that are way below the wing are barely going to fly under, and the ones that are way above the wing are going to fly above, mostly without being disturbed by the wing. But what's going to happen is you're going to eventually get some of these that are going to try to hug the surface and go over the top, and some of these that are going to kind of like impact and then kind of like go down below on the bottom. And I'm going to talk about why it hugs in just a second. But the thing that I wanted to really point out to you is that right on the nose of this thing, what you don't often get taught when you learn how these things work, is that the wing is ramming into the air at 200 miles an hour, whatever speed you're flying at. And what ends up happening is it's compressing the air in front of the wing. So that's what I'm trying to draw with the purple right here. Compressing, right? And it's usually pronounced a little bit more on the top than on the bottom because the way the wing is oriented. But there's a high pressure region right here because of that. Okay, so I'll say that this is compression. And because of that, there's kind of like a high pressure region right here. Now, what do you think is going to happen to the area of the wing over here? Now, I want you to kind of use your imagination here. Use your hand as if you're holding it out of a car window. By the way, disclaimer, don't do that. But if you did, you would feel the wind hitting your hand, pushing your hand up, just like an airplane wing. See, you've already done it. You've stuck your hand out the window and you've surfed it. So you know you generate lift just with an angled hand, okay? Now, the area right on the backside, shadowed, for lack of a better word, from the relative wind, shadowed, this area here. The wind is compressed right here, and it takes time to flow over, right? It's not like the speed of light. It takes time to propagate backwards. So right here, you might think of it as kind of like a vacuous region or a vacuum region. Or if you don't want to use the word vacuum, just say that this has to be a lower pressure than this because this is compressed, and this is certainly not compressed because it's on the backward side of the wing, right? So what you could say is that this part is like the shadow. And when I say the shadow is if you shine the flashlight here, then this would catch all of the light, but over here would be total darkness. The light would, of course, never go there unless it curves around, which it does. I'll explain why in a minute. And so this is lower Pressure. So you know you have a high pressure region because the front of the bullnose of the wing is ramming into the airflow. And you know you have a lower pressure here because it's not being rammed into the front part of the airflow. And because there's a high pressure here and a low pressure here, that drives the airflow and accelerates it over the top of the wing. And that is critically important. That is what you're not taught, or one of the things you're not taught about how wings work. You're taught that, oh, it just magically splits and it has to end up at the end at the same time, but you're never taught why, and the reason you're not is because that's not a law of physics. It's not even true. But what you can be taught is that you're compressing the air, high pressure in front, lower pressure here. The difference in the pressure causes the airflow, when it comes over the top here, to see that lower pressure and be sucked towards it or pushed towards it, however you want to think about it. And that is the real reason why the airflow is faster over the top than over the bottom. So to rephrase it another way, it's not that the airflow is faster over the top and because of Bernoulli's equation, the pressure then becomes lower. That's not it. It's that because of this pressure difference, the airflow is accelerated over the top into the low pressure region, and the velocity of the flow is faster, being sucked into the low pressure region, for lack of a better word, and then through it and then off to the back there. So it's not that the equal transit theory causes low pressure. It's that the low pressure region forms because of what I'm talking about here, and that accelerates the airflow over the top. So it is true that the air flows faster over the top, and it is true that there's lower pressure on the top of the wing, but the cause of which one is causing which is a little mixed up, in my opinion, with the traditional way of teaching that equal transit method. So there is lower pressure on the top, and of course, this is higher pressure, and this is exposed to mostly atmospheric pressure, and there's some flow here as well, but not as high a pressure as this, but this has to be higher pressure than this as well. So this can be thought of as higher pressure. Not as high pressure as this, but it has to be higher pressure than this. This is in a shadowed region, not even encountering the air until it gets over the top. This is encountering the air without that disturbance. The bottom is shaped differently than the top. The airflow is basically coming in and smashing into the bottom, reflecting off the bottom, generating lift of its own. The pressure here is higher than the lower pressure here, which is kind of shadowed and hidden from the relative wind coming over. This pressure difference generates, or at least one of the components for lift of the wing. But notice there's more than one reason why the wing is lifting. It's lifting just because the bottom surface of the wing is literally redirecting the airflow, causing a reaction force pushing up. So part of the lift comes from the air just bouncing off the bottom. And another part of the lift comes from the fact that there's a low pressure region on the top caused by what I've been talking about here, that it's kind of in the vacuum region, for lack of a better word, behind on the backside of the wing, away from this high pressure region there. So you have high pressure, highest pressure, low pressure. And the difference in these pressures generate a lift vector as well. So you might think of part of the lift in the red coming from the pressure difference across the bottom and the top surface of the wing, and then you might think of another part of the lift coming from simply bouncing air off the bottom of the wing, like this, generating a reaction force going up. So there's a component of the lift coming from the pressure difference across the top and the bottom, and then there's another component of the lift just because the bottom of the wing is bouncing airflow down, changing its velocity, which is a change in the momentum, and any change of momentum is accompanied by a force. And because you have a force pushing the air down, then the air must have a reaction force pushing up. Action, reaction. Okay? Now I think I'm in a place where I want to expand on what I wrote here, that any change in momentum is accompanied by a force. And I'm going to do that real quick for you. Remember from physics that the momentum of a particle is its mass times its velocity. Okay? So what we can do is use calculus. If you haven't taken calculus, it's okay. I'll explain it in words, so don't stress out about it. But we can take the derivative of both sides. We can take the derivative of momentum with respect to time. That's the change of momentum I wrote down here, right? And we can take the derivative, like in algebra, you can take the derivative you can add 1 to both sides, you can add 5 to both sides. Well, I'm going to take the derivative in calculus to both sides. But what you know is that the mass of the particles really is not changing very much, so the mass can come out of the derivative, and so what you're going to have is the m dv dt. So the change in momentum is equal to the mass of the particle, whatever particle is interacting, times the change in the velocity stream, right? Redirecting the velocity stream. But if you remember from calculus, the change in the velocity is equal to the acceleration. So basically what you figured out here is that dp dt, the change in the momentum, is equal to mass times acceleration, when you already know from Newton's law that force is equal to mass times acceleration. So before I told you, I said, hey, believe me, don't worry about why, but anytime you change the momentum stream of a stream of particles, it's accompanied by a force. Here I'm telling you why. Because if I take the derivative of the momentum and ends up becoming a derivative of velocity with the mass coming out, then it becomes ma, which is the same as a force. So the change in any momentum of a particle stream is accompanied by a force. And so whenever the flow bounces off the bottom, you can think of the momentum or the velocity vector, momentum vector, however you want to think of it. The momentum is changing direction from horizontal to, at least a component of it, is vertical. That change in momentum must be accompanied by a force. That's what directs the stream down. That's what bounces it off. The wing is slapping it and pushing down, but then the stream must be pushing up on the wing. That's this component of lift from the bouncing off. Then you have another component of lift because there is a higher pressure on the bottom than the top because this is in a shadowed region from the relative wind and the flow is accelerated over the top. All right, now I want to talk about what might be, in my opinion, the most interesting part of all, because we're not actually done. That's not actually all of the reasons a wing generates lift. Have you noticed a phenomena? If you take a spoon and you put it in the flow of a stream of water, like in the sink, oftentimes you can catch the flow where it'll take the water and the water will stick to the surface of the spoon, for lack of a better word. It'll follow the contour and then it'll kind of spray out into a beautiful spray. Right? There's a word for this thing. It's called the coanda effect. And it's a thing you learn about in fluid mechanics. Basically, in general, fluids with viscosity is a word you might have heard of. Thick things like oil have high viscosity. It's like internal friction between the molecules. I'm going to talk more about it in just a minute. I told you we were going to get down into the molecules here. All right, so you have internal friction called viscosity. And when you have viscous liquids like that, they tend to stick to surfaces at least a little bit, almost like surface tension kind of, as they pass around objects. A better way to maybe visualize it is if you have like a baseball or throw a baseball through the air, if you could look at it in a wind tunnel, you would see that the air would be, hitting it from this side, let's say. Some of the air would go like this and hug, maybe detach over here. Some of the air would go and maybe hug like this, right? But why does it hug the surface, right? Because that's also happening here. I haven't mentioned it, but we're going to now in great detail. When the flow gets rammed here into a high pressure region, it bends up and it follows the shape of this thing. It follows the curve of it down to the rear end where it detaches and goes off into the atmosphere. Why does it follow the shape of why does it follow it at all? Like, if you think about it, why doesn't it just go and then go straight? Why doesn't it just detach and go straight? Well, it's because all real fluids have some kind of viscosity. The only ones that don't are really weird fluids, like liquid helium is extremely weird. No one here is dealing with liquid helium. But water has viscosity. Air, oxygen, air is consisting of oxygen, O2, nitrogen, N2, carbon dioxide, water. They all have some kind of viscosity, although less than water. I'm going to talk actually why viscosity happens as part of this. But for now, you can imagine the flow hugging it like this. So this has a word, and this word is called the coanda effect. Coanda effect. And basically, it's the tendency of fluids to stick to surfaces when they float around like that. Like I said, with the spoon or with balls in there, in this case, airplane wings like that. And the reason I'm bringing it up is because the fluid is hugging the surface. Notice that the wind stream has a parallel velocity vector horizontal. But what happens is it sticks to the surface of the wing and it gets bent down. So when it exits the wing over here, the direction of the wind is not horizontal anymore. It is down, angled down. Say it again. It's now not horizontal, angled down. Whenever it hugs the surface and then it exits, it's angled down, saying it a lot. Remember what happens when you change the velocity of a fluid or changing the momentum vector or direction of a fluid from horizontal to down. Any change in momentum or velocity must be accompanied by a force. So by directing this airflow and pulling it down across the surface of the wing through the coanda effect, you're changing the airflow from going horizontal over the wing to being tilted down, almost like a rocket engine. And action-reaction on that part of it is also generating a force in the up direction. That's critical. So there's like 3 different reasons so far for lift. One of them is bouncing off the bottom. One of them is a difference in pressure from the bottom and the top. And the other one is that the wind is hugging and sticking to the top of this surface and being angled downward. From horizontal to downward, that change in velocity has to be accompanied by a force. Basically, the wing is pulling, literally pulling the airflow down to curve it. That's an action force, is the wing pulling down on the wind. And the reaction force is the molecules of the air pulling up on the wing. That is another component of force there. That comes from the intermolecular attraction between molecules. All right? But of course, I could leave it there. I could just say, believe me, bro, it just does it. I don't want to do that. That's no fun. Why does it stick to the surface of the wing? You see, you can ask questions forever. Eventually you get down to quantum mechanics, and that's what we're going to do today, right? Because this is what I find fascinating. Why does it stick? Why does fluid seem to stick to surfaces? Well, in order to explain that, you have to talk about the molecules. You have to talk about what's actually happening down at a deeper level. So let's start by this top level picture of the wing, and let's zoom in just to the surface of the wing. This flow tends to stick and follow the curvature of the wing and become redirected downward. So we have to zoom in a little bit of a level there. So let's draw the top surface of the wing. I could draw like, this is like the wing structure or whatever, and it's angled down. The bull nose, I guess I could do something like, you know, the bull nose is here and whatever. This is the trail. But all I want you to look at really is this. All right, there is a thing that you learn about in fluid mechanics called the no-slip boundary condition. When you have a fixed surface and a fluid moving across it, this could be inside of a pipe with water flowing in it. It could be across an airplane wing. It could be across whatever. It could be across your fan spinning in the house, okay? Anything moving through any fluid. The velocity of the fluid just touching the surface actually is 0, right at the surface. I'm talking about 1 molecule thickness or whatever at the surface. So basically, you can think of the individual water molecules or carbon dioxide molecules. I'm just drawing them as balls because I don't want to draw the structure of each individual molecule. They get stuck to the surface through friction. The real reason is electrostatic attraction from the molecule to the atoms of the surface of the wing, in our case, okay? But these red ones here are not moving. The velocity of these things is 0. They're stuck there, like 1 molecule thick, let's say. Now, don't forget the wind is rushing over the top. So what happens is the layer directly above, this purple layer, right, has a velocity which is like this big, let's say. A little bit bigger, but not 0. And then the layer of air molecules directly above that has a velocity bigger. And can you guess what's going to happen? The layer above that has a velocity much bigger. And what happens is eventually the velocity approaches 0 right at the boundary, and then you get far enough away, you reach what's called the free stream flow. That is what is happening to the flow far enough away from the wing that it's not really being disturbed by the wing anymore. Then the velocity would be at however many knots you're flying at, like let's say 100 knots or something like that. But as you get closer to the surface, the velocity is getting lower and lower and lower. How does that happen? Okay, well, the innermost layer is attracted because of electron clouds, basically, to the surface. So they're motionless. Right above it, there's some momentum. It's trying to scrape by, and they're being attracted to the layer underneath. So they're slowed down, but not all the way to 0. The layer above that is slowed down relative to this layer, but a little bit faster. And basically, each layer is dragging on the layer above it until eventually you're far enough away so that the surface of the wing is not influencing anything anymore, and you're getting to the actual free velocity flow of the free stream velocity of the bulk flow that's above the wing there. Why am I bringing all this stuff up? Well, because this thing is called a boundary layer. Boundary layer. And this is essentially what is the cause of this coanda effect. You see, everything builds, right? I'm like, okay, these are the reasons for lift. And I'm like, okay, this thing's hitting this, and it tends to hug the surface. This is one reason why we get lift. It's hugging the surface, and it hugs and hugs and hugs. And I show you, hey, haven't you seen the spoon with the water? And it kind of hugs the surface. Doesn't that kind of behave like that for water? Okay, and you're like, yeah, I remember that. And then I show you, hey, haven't you seen like for a baseball, like the air kind of hugs as it go over, and you kind of start to accept it. And if I just stop there, then you will just believe me that the coanda effect causes the airflow to be redirected downward, which is a change in velocity, change in momentum. That means there has to be a force applied. That's the wing attracting the flow downward, and the reaction force means the flow must be pulling up on the wing. That's another component of lift. And I could leave it like that, and that's fine. But why does the coanda effect happen? Okay, the coanda effect happens because of molecular attraction between molecules and between the molecules and the surface of the wing. One thing you need to kind of accept is that when you get two atoms next to each other, a lot of times they're going to attract, at least weakly. Almost all atoms attract between each other. And so when you get down to brass tacks, this atom of the metal and this atom of the nearest of the air there, whatever molecule it is going to have an attractive force there that comes from the quantum mechanics of their electron clouds. Once this one's stationary, then the one above it is going to be dragged a little bit more and a little bit more until finally the velocity of the flow is greatest far away. So this force of attraction is what is bending the flow downward, is what I'm trying to say. This over here is a thin boundary layer here where the molecules are totally stationary and they're attracting the flow going over the top. And the boundary layer, if you could draw it, would be super, super thin. The boundary layer all the way across the top of this wing, essentially motionless air. And then it's going to be attracting the air over the top and literally pulling it down, almost like a magnetic kind of attraction. But it's not magnetic, it's an electrical attraction between the atoms themselves. So, again, I could stop there. I could say there's this coanda effect. It's attracting it. It's pulling it off. Eventually, it's pulling the flow down. Eventually, the flow ends up with a velocity like this as it exits the tail in like this. And that means there has to be a vertical velocity component and a horizontal velocity component. But I changed, it was purely horizontal, and now it has a vertical velocity component. So I must have changed its momentum. Therefore, there must be an action-reaction pair, and so that's part of the lift. But then let's go a little bit deeper. Why do the atoms in the molecules actually attract each other? Because that's the reason for the fluid mechanics sticking to the surface in the first place. All right, there's a bunch of different reasons. Let me go get a prop and I'll show you. All right, this is water molecule. Water does exist in the air, but I'm starting with water because it's easier to understand, I think. And you know, you play with water all the time. And you know water has like this surface tension thing. You kind of have a lot of experience with water. So here you have H2O. Oxygen actually attracts electrons a lot more readily than the hydrogens here. And this black stick is a sharing of electrons. This oxygen here is pulling the electron clouds. They're shared, but they're not shared equally because the nucleus of the oxygen can pull the electron cloud a little bit closer to the oxygen. So really, water is what we call polar. The oxygen side of the molecule is a little bit negative, and the hydrogen sides are both a little bit positive. And the reason is because that electron cloud is pulled away from the hydrogen a little bit, revealing its positive nucleus a little bit. That's what gives rise to surface tension also. So there's this thing called hydrogen bonding. This is what I'm describing. And whenever two water molecules come together, since this is a little bit negative, and the other molecule that bounces into it, the hydrogens are a little positive, it's going to be slightly attracted. This thing will be attracted to the hydrogens of another molecule momentarily until it can bounce off and get away. But there's a little stickiness to the water because when they bounce in such a way that this white ball touches another red ball, they tend to want to hold each other, but then they bounce off. There's a little bit of internal friction or resistance to it because of the charged nature of water. So that is called hydrogen bonding, and it's an intermolecular force. Okay, it's because oxygen's so electronegative and the hydrogens aren't. Now, what do you have in air? Air is some water, but mostly it's nitrogen. Two nitrogen atoms and one bonded together. And you also have oxygen, O2, bonded together. So I didn't have different colors, but this could be like nitrogen. This could be like another nitrogen molecule. There's an electron cloud surrounding the nitrogen atoms. And if there's an oxygen atom in its molecule, there's an electron cloud surrounding those as well. Let me draw it for you real quick. Here's oxygen. There's a double bond between oxygen. And here's nitrogen. And there's a triple bond between the nitrogen. I'm not going to get into the bonds and why they're triple and why they're double. But for nitrogen, there's an extra 2 electrons that are kind of like hanging out with the nitrogens over here. And in oxygen, there's 4 electrons hanging out on each of its guys here. In order to understand this, you'd have to go to the periodic table and see how many electrons there were and how the shells all arrange themselves. You have to, at some point, stop digging and just trust me that oxygen has a double bond with extra electrons here, and nitrogen has a triple bond with extra electrons here. But these electrons in quantum mechanics are a little bit weird. The electrons are not like dots that stay right here, even though I've drawn them that way. They're not. It's more of a cloud that kind of like envelops the whole thing. And the cloud is a probabilistic thing. Spontaneously, sometimes the cloud shifts one direction, and then it'll bounce back and shift more to the middle, evenly surrounding both of these guys. Sometimes the electron cloud will shift kind of like this way and be more around this nitrogen, and then it'll shift back. All of this is happening at the microsecond scale. Nothing you would ever even be able to really see with your eyes, but that's what the theory says. All right, so let's say that there's another oxygen molecule nearby. All right, and momentarily, just through statistical fluctuation, what happens, let's say, is that this electron cloud envelops the right-hand oxygen molecule a little bit more than the left. And that means that there's more electron, so this would be negative side, and this would be positive side. This is like jello jiggling all the time, sometimes over here, sometimes over here, sometimes up here, sometimes over here. But in this nanosecond of time, it's a little more negative on this side, but it encounters this guy here. The negative side of this cloud repels the electron cloud surrounding this one and making it do the same thing, be a little bit lopsided. So that basically this is the positive side, and this is the positive side, and this is the negative side. Basically, the negative charge density here repels the electron cloud, pushing it away, revealing the positive nature of the nucleus here, and then attracting it. But because it was all a random fluctuation, as soon as that attraction happens, they stick together a little bit, and then it fluctuates the other way, and suddenly these clouds look different, and then they're not attracted anymore. This is happening all the time between molecules. This is called London dispersion forces. It's a type of force between molecules. Most molecules attract each other to some degree, some more than others. Water molecules attract pretty strong because they're very highly polar, like I told you. But this oxygen molecule is not polar, and the nitrogen molecules aren't polar, but just because of the shifting nature of the electron clouds, they can attract each other briefly, and then that causes an internal friction or internal resistance to happen. So I'm just proving to you, using electron theory, that molecules, even when they're not charged and they're not polar, usually slightly attract each other all the time. And what is happening as the airflow goes over the wing here, this molecule, which is more or less stuck to the surface, is attracting these. The reason it's attracting them, even though they're not charged ions, is because of this stuff. All bulk fluids like this usually have some kind of attractive forces inside the fluid. And this molecule is literally pulling on this molecule here. And this molecule is literally pulling on the one above it, and this one's literally pulling on the one above it. So the force acting down on the air above is like the wing. It's kind of coming from the wing. It's like the wing pulling down on the air. That's the action force. With every action has an equal and opposite reaction. Pulling down on the air means the air must pull up on whatever's underneath it, which is the wing, and that is another component of the lift. So just to pull it into a bow, okay? 3 ways this thing lifts. One is because it bounces off the bottom. That's a change in momentum, means action-reaction, and the lift vector is up. Then, because of the compressed air here and the accelerated flow and the shadowed area back here being in lower pressure compared to this, that's a difference in pressure generating a lift upward because of the difference in pressure. And then finally, fluid flow splitting like this tends to hug the wing and be directed in its flow downward. That's a change in momentum of the flow, being directed from horizontal to a component of vertical. That must lead to a change in momentum, which must lead to a force, which must lead to action-reaction, which is another component of the lift up. But when you dig the situation deeper, why does it stick to the surface? Why does it want to be pulled down? Because of these intermolecular attractions of the different layers right near the wing surface. And now you know when you really look at the structure of an airplane, the wing is not usually perfectly horizontal, it's usually tilted up a little bit, and when you see an airplane flying, it's usually tilted up a little bit, like this drawing, to get the benefit of the lift coming from the bottom, the lift coming from here, and also the flow, you want it to stick to the surface. What do you think's gonna happen if this is your wing, let's say it's nice and rounded like I have right here. This is my rounded wing, right? And now I'm gonna pull back and back and back, slow down, slow down. The wind is going to be able to hug the surface, hug the surface, hug the surface, but when I get too steep, if I get too steep, it's going to detach and it won't hug the surface anymore if I make this thing too steep. Then it's going to curlicue, which is a vortice or an eddy current, and it's going to detach here. And when that happens, you generate a lot of drag, and then you're also not directing the flow down anymore. Remember, it's directing the flow from horizontal into a downward direction. Almost think of it as a rocket exhaust. The rocket has to blow the exhaust out the back to go the other way. The wing has to attach the flow on the top to direct the flow down so that you get a downward velocity vector, which generates part of the lift. But if you pull the angle of attack so far up that the wind, these molecular forces that are pulling it down are now not strong enough to pull it down, then you get detachment of the flow. And of course you get the drag from that, from the eddy currents, but bigger problem is that the flow does not follow the wing trajectory anymore. And so you don't get the downward angled velocity vector, and that destroys a good chunk of your lift. So whenever you really are flying an airplane like this, and you pull back, you can feel it. It shudders, and then it just drops, and then the nose usually tends to go over. And if one wing stalls before another wing, you can get into a spin, which is a whole other can of worms and much more dangerous. Well, as you might have guessed, I'm pretty passionate about this. I spent my own money to learn how to fly airplanes a long time ago. I've always enjoyed it. I like it. Haven't done it in a while. But I wanted to bring my knowledge to you. Now, please write me. I'm sure that people are watching this and they're really get wind tunnels with wings and tell me that I could have expanded on something, or maybe this wasn't as important or whatever. That's okay. I'm fine with that. Please drop me a line. Let me know what you think. And also let me know if you like this level of detail, because I certainly did not need to talk about London dispersion forces to explain this coanda effect of hugging the surface of the thing. And now you also know why, when you're in 6th or 7th grade or whatever, and you learn why an airplane flies, they don't tell you all this stuff, because it took an hour here, and I can still talk and talk forever. And so we learn that there's an equal transit theory, and there's low pressure on top and high pressure on bottom, and that generates lift because that's digestible, and it conveys a lot of the core ideas. You really do learn from that there's low pressure on top and high pressure on bottom, and it conveys a lot of important things. But I wanted to go into the weeds and discuss the details, mostly to get it out for myself and also to see what you think. So please do drop me a line, let me know what you think, and as you go forward and get into an airplane and go flying, don't forget to stay curious. Learn anything at mathandscience.com.